linear independence between the solutions. Okay. Linear independence. So we will make an example of the second order ODE first. Then we will expand that to be a general higher order linear ODE independence, a linear independence. So for example, for a second order ODE, linear ODE, the solutions between y1 and y2, solution for a homogeneous solution YH, x will be equals to y1x and y2x. Okay. And you know that is a linear combination with some constant. You can say C1 and the C2. So that is the general form of your second order linear ODE homogeneous solutions. If my y1x divided by y2x is equals to a constant that is linear dependent. Okay, and if my y1x divided by y2x is equals to some function of x, that is called linear independence. Okay, and for more general form that dyh equals to C1y1 plus C2y2, and this C1 and C2 are the arbitrary constants. Then how we decide, you know, whether they are linear or independent in a more general form or more general form. Let's make an example of the second order ODE. So if my y1x and y2x are linear independent, then we can write yh prime x equals c1 y1 prime x plus c2 y2 prime. And to evaluate x equals to x0, we can write this as a matrices. We can write as y1x, y2x. This is y1x prime. So we evaluate at x equals to 0. This is y2 prime x0 times the constant, which is c1, c2. That will be equals to our y x0 and y x0 prime. Okay. And for this system, if this system to be non-zero system, this constant will be non-zero, right? Because you need to have two linear independent solutions. So the constant is not 0. Then in order to make this equation as a non-zero solutions for the system, to be non-zero, or you can say this is non-trivial. It's the same thing, non-zero equals to non-trivial. Then what we need to have in order to let this equation to be non-trivial or non-zero, we need to have the determinant of this part is non-zero, okay? So the determinant of y1, y2, y1 prime, y2 prime is non-zero. And in order to calculate the determinant, which is y1, y2 prime minus y1 prime, y2, is now 0. So this determinant has a particular name. This particular determinant is called the Wronski of y1 and y2. So in order to prove your y1 and y2 are linear independent solutions, you need to have this Wronski determinant to be non-zero, okay? So this Wronski y1, y2, which represent by this determination, is non-zero. And for that is the conditions for y1 and y2 are linear independent. And for a higher order, linear ODE, the Wronski matrix can be written as higher dimension, y1, y2, dot, 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 to yn, will be equals to y1, y2, dot, 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 yn, y1 prime, y2 prime, dot, 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 yn prime. Then this will be y1 n's prime, y2 n's prime, dot yn n's prime, and this won't be equals to 0. Then we can say for nth order linear ODE, our solutions, homogeneous solution y1, y2 until yn are linear independent. Okay.